Okay. Hello, everyone. I'm Aleksei Menshutin, and I will present my work about path minimal objects in ArkTS symbolic execution. The idea is the following. We want to construct TypeScript executable tests from path constraint harvested during symbolic execution in ArkTS applications. A bit of context, a bit of motivation. Why do we need it? My idea was to create a helpful tool for a family of languages like JS, TS, and particularly ArkTS. It's a language created by Huawei. I'll speak about it a bit later. And the main issue for these languages is they are dynamically typed. So, for example, we can see a function foo, and it accepts argument x with unknown shape. It might be a number, string, boolean, some class A, which is also has unknown shape, or even undefined. So we have an issue that in many cases, we have either really complicated types of arguments or even unknown. And we have no option for static analysis to understand what exactly the structure of these objects will be. This is extremely common in real code and makes analysis very difficult. As a result, we have really complicated control flow. It depends on some property membership. That, for example, some property is presented in some object. For statically typed languages like Java or C#, it's really something really new compared to them. We have complicated type checks like type of, instance of, some really strange and confusing coercions, different equalities, and so on. We have delete and nested accesses. For example, when you can delete some properties from an object, or when you can add some properties and create really deep nested objects. All of this influence on analysis we have. Here we can see a small example where we can mix all these checks. So for example, in the first branch, we did check that the property X exists in this object O of any type. After this, we check if it's a number and it is a none, the none. We can return it, return 1. And after this, we have check about equality with 0 with unclear coercion, because as we know, O.X might be any type in the program. So it's not only number comparison, but maybe with some unclear coercion. And in any other case, we return 3. And this complicated logic makes it complicated for different analysis techniques, for example, like data flow analysis, to go through such programs and create robust results with a quite high certainty rate. Why symbolic execution? My idea was to provide extremely powerful and extremely expensive analysis technique for this problem. So for each path, we can have an explicit quantifier-free condition. After this, we can solve using some SMT solvers and something like this. And we will have reproducible reproducible inputs that we can have to test on. So we can have small tests that will reproduce some maybe bugs in the program, or just reproduce some behavior we want to have. It's quite good for my two main directions in my point of view. The first one is test generation, where we can use symbolic executor as a test generator. So after this, we can create a regression test suite to fix our behavior. And the next one is checking path feasibility for other analysis. Actually, it's the main purpose of this engine I created, is to check the results of another analysis, because this another analysis quite fast, but produce many false positives, and we want to check which one of them are real ones. But in practice, we have two main issues. Symbolic execution, even for static languages, has many issues, but here we have two additional ones. The first one, we need to correctly encode the dynamic semantics in the SMT. It's quite challenging. And the second one, since we can put any values in the object, we want to create these objects as small as possible in terms of properties they contain. So we want turning models into small, robust test inputs. For example, here we can see a function foo, which just takes x property and returns it from the method. And it doesn't need information about any other properties of the argument it takes. But we can see that in real world analyzers or fuzzers or as other test generators, they may produce brittle, big structure for these input objects and pass it into the method. And it has three main issues. It makes test harder to read because more symbols, it's harder to understand. It can hide some missing checks or missing properties because if it became more complicated, it became more complicated for you to understand it. And the next one, it makes regression suit fragile. It means that when you change something, this test might broke, not because its test checks broken, but because of some accesses or something like this. Now a few words about ArkTS and ArkAR. ArkTS, as I mentioned, is a language developed by Huawei for its phones, PCs, routers, and all other many products of this company. And it's an extension superset of TypeScript with some differences. For example, in TypeScript, you have structural equality, so you can pass methods with the same fields, even if the declaration explicitly prohibits you to do this. For example, in method foo in TypeScript, you can pass d as well. But in ArkTS, it's a compile time error, and ArkTS has also several other restrictions compared to TS and especially JavaScript to make applications more reliable, to make it work faster, more with more precision and more reliable. And ArkAR is an intermediate representation for this language. It's provided for us by ArkAnalyzer. It's a tool from the same team that creates ArkTS. And the pipeline for us is the following. We have ArkTS or TS and even JavaScript source files, or probably ArkTS bytecode, because ArkTS is compilable language and you can compile all these files into one ABC file. After this, using this ArkAnalyzer, you can get ArkAR. It's free address, control flow graph-based intermediate representation. It's universal representation for both compiler and source code level, so that's why we use it, because we don't want to make different analyzers for different representations of code. And ArkAR already has explicit control flow edges, some instructions for reads, writes, deletes, assignments, and so on, and optional type annotations. So for example, it's annotated AR, type annotated AR. So you can have your own types or types provided you by some type inference or provided by programmers, and you will see it in your intermediate representation. Or you will see ETS unknown type if there is no such information. So the idea to working on this level, it's important because we not just want to work on TypeScript or JavaScript, we want to make analyzer for the whole family of languages. And it allows us to do this. It's a good compromise between high-level code like JS and TS and lower-level ArkTS bytecode, because it operates with really simple instructions and we don't want to reproduce all this logic. Unfortunately, as I mean, also I mentioned that ArkTS is quite strict language and it prohibits many like undesired behaviors. We can also compile with its compiler JavaScript and TS file. So all the issues we had in these languages are still stands. Type absence, property manipulations, structural typing, etc. So we have to deal with them. And now let's go to the main two practical problems we want to solve. I mentioned the first one is to encode dynamic semantics into SMT. So what do we need to encode? Heap and aliases. So we want to create heap symbolic representation for heap memory. We want to reproduce creation and deletion of properties, because in other languages it's impossible. So it's some unique feature for these languages. Strict and unstrict equality, some creations, exceptions, short circuit logic, because it's a bit more complicated in JS as well, truthy types and so on. So some unclear properties of these languages. And the second one, we want from SMT models, where we can have interpretations on all the symbols in the program. We want to create not over-specified objects. We want to create minimal objects. We need to have minimal inputs, pass minimal objects for these tests. A bit example, what I mean by pass minimal objects. Naive approach would be the following. If you need to have some input for some property, just put everything you can in this property. So all interpretations of the symbol. We know that SMT models can contain any interpretation for any symbol in the universe. So we could have all these properties calculated, but it will make so many fields that are relevant for this path. And it completely removes the benefits of precise symbolic path, because we cannot understand if this object is what identical for this path. It represents it, or it's just a random objects in the system, and we are lucky to have it. And our approach in a high-level idea is to symbolically execute ArkTS under JS-TS semantics, and to make it work on real-world applications, because real-world applications is quite large. We want to have some novelty approaches. For example, due to performance, we maintain two coordinated channels of constraints. So we separate SMT path constraints, for example, limit the conditions on numbers, booleans, and so on, and typing component tau that stands for instance of, dispatch regions, classes, subclasses, and so on. For example, at the picture, we can see function foo that takes x argument as a number and y is of any class. And in the program, we can see that we created some path typing constraints, which is a y instance of number, and some logical constraints about equality of the numbers. For each satisfiable terminal path, that means that we go from the beginning of the program to the end of the program, we solve these path constraints using some solver. We extract these path minimal inputs for primitive, just the primitive itself. For objects, it's minimal by a number of its properties, and we optionally emit just style tests. So for example, for this exact example, we have path constraints that x is equal to y and y is a number, and we have interpretation of it. We have model with both values are equal to 0, and we know that if you pass these values into this program, you will have return 1 result. So the whole pipeline looks like this. We take an entry function of these languages. It can be any of them. We obtain ArkTS from either source or ABC file, doesn't matter. We symbolically explore feasible terminal paths, return set exceptions, and for each path, we submit path constraints to a solver and get model M. From path constraints in this model, we construct path minimal inputs, and optionally, it's not required, we can generate test inputs, test outputs for our users. Of course, symbolic execution on ArkTS encountered enormous number of issues and complications, and in few words, it operates with the main primitive. It called symbolic state. It consists of three main parts. Current instruction in the control flow graph we analyze, symbolic memory, it's stack plus heap of the program, and path conditions, it's conjunction of two components, p and tau. Heap is represented with object addresses, which is an uninterpreted sort. So an uninterpreted sort is an entity that can be compared on equality only. So they don't have order on something like this. They can only be compared about equality. We create per-field arrays that allow us to support aliasing, and we create membership atoms. So it's Boolean atoms about that some object O has key. So for example, if we know that object O must have key X, that means that it should return the exact value, not undefined. And we can create the corresponding symbolic expression for it, that V is equal to reading from the memory if this object has this field or undefined otherwise. This behavior corresponds to ECMAScript specification. Inputs can have sometimes unknown type, because also we have typed language, but you don't need to obligatory specify it, since we can compile it from JavaScript, for example. So we need to somehow symbolically represent objects with unknown structure. This is the novelty of this article and this work, the way you can efficiently encode this in the SMT. So for each object, input object with a unknown type, we create some fake values encapsulating all possible primitive it can contain. For example, we can have that x is equal to fake value with some symbolic primitives x, y, xb, xr. And how to understand what primitive we need to use? We need to encode its type. It's a union of num type, bool type, and ref type. And encoding this into some ifs and else expressions into SMT, we can make it work fast enough, because otherwise we would need to work on different behavior and get path explosion really, really fast. So now we have shown a few words about different path constraints. As I mentioned, we have type information, tau. It's information about type of, instance of, annotations, class hierarchy. So all the information about class structure. It's not about the exact fields we have. It's about class structure. For example, that object X constructed by constructor number, and so on. It lives in a lightweight component tau. It's not encoded into SMT. We solve it by our own type solver on our side. It's used for proving invisible forks, resolving virtual calls. So it's not about these path minimal objects. It's about symbolic execution itself. SMT path condition, it does not consist it isn't consist of any class or subtype predicates, so it doesn't have a type information. It consists of numeric Boolean bit vector constraints, some values predicates, like I mentioned previously, and these Boolean property atoms and guarded reads. So information about these path minimal objects. Which property do we need to have in this program that we still can satisfy the following path? And about these path minimal objects, consider that we have one satisfiable path. So the path we can go through the beginning of the program or the beginning of the function we started to analyze to the end of this function. We have some path conditions, p and tau, and the model that satisfies them. For each entry object O, we look at the keys of this object, and if we have this property Boolean atom in our path condition, that means that we need to have it in the resulting object. And we keep only this key that is required for this satisfiability. So our result, our path minimal object, contain exactly the required keys. So if you remove any keys of this set, we will have unsatisfiable path. We use these values from our model, so all the values also satisfy this path, and it does not contain anything else. It's more, it has more information in the article, so we have it by construction, that we don't have anything else except of these atoms. It's a bit of formalization of what I just said. I don't think we need to stop on it, only if we will have some questions. And from this model, we create the path minimal objects, like I mentioned. removing any key from this object will break the path. In path writes and deletes do not become entry obligations. It means that if you can remove properties, you can add properties, but this will not become an obligation for this object and will not influence of the object shape. And it's independent from how DAO decides class or subtype constraint. So for example, if you have some class A and it doesn't have in its declaration some property X, if somebody ask you that this entry argument should have X as its field, it will be presented in this object. And some examples about what I just said. So for example, we have two functions, f1, and we can see that what are path minimal objects for it. So to satisfy the first path that returns 1, we need that object O must have property X and type of this X must be number. And we can see that the success of path minimal object for it is just an object without a name that contains this X. And the second one might be everything else. So the path minimal object for it is just an empty object. In opposite, in F2, we have a path that specifies that X should not be in O, and this is an empty object. And for the second one, we can see that it's X of type anything. So it can be everything, and symbolic execution understands that we don't have any limitations for its type. So PMO highlights exactly which keys matter for each branch. It makes easier for programmers to understand what they need to look at in a particular test. The next one is a bit more wordy, a bit more complicated. So we have some type coercion and checks for none. In JavaScript, undefined +1 is none. What does it mean? That means that to satisfy the first path of the branch, actually, we don't need to create any none values, any objects, complicated structure, any fields. We can just create empty object, because after we read X field from an empty object, we will have undefined. Undefined +1 is none, and we will have successful check. Number is none, and return 1. So the path minimal object for this example is empty object as well. Other tools might create some complicated structure to understand that we need to have some field of undefined or something like this. It's not required in this example. And alternative path is satisfiable if we will have X property of non-undefined value. For example, X might be none, and in this case, we won't have none value after addition, and we will have the next path satisfied. And a small example that delete is not create path obligations. So if we delete some property or create some property in the first line of this method, it doesn't mean that this object all must have it at the beginning of the method. So you can modify it. It doesn't matter. It does not affect path minimal objects. So the results of this structure, this article is the following. Now we have ArkAR level symbolic execution for ArkTS, TS, GS. We have some novelty about split constraints. It helps you to provide more flexible structure and more flexible solving of these equations, and they work faster because it's quite expensive to encode everything into SMT, but you can encode it into your own structure, and using some semantics or some knowledge about language, do not encode it into SMT and solve it more efficiently. We implemented path minimal objects, which is minimal by fields inputs for each path, and they are used to generate small jest test TypeScript tests. Limitations of the work, of course, we have several limitations. The main one is the current evaluation is qualitative. So we don't have quite big benchmarks. We don't have numbers on real projects because it's quite complicated to measure, and we haven't done it yet. So we don't have large-scale benchmarks. Another one is language support. Also, we supported enough to work on real projects, and even large real projects, it's not enough to implement all JavaScript, ECMAScript specification. So we don't have the exact support for modules, enums, proxies, symbolic property keys. It's in progress, so we have partial support for all of it, but not complicated one, but not complete. And some practical directions I see for this work, it's integrate this PMO-based tests into CI, use them to validate alarms from other analyses. Actually, we already use it right now. Expand ArkTS instructions coverage and real-world projects, for example, for benchmarks, and improve test oracles for floating point corner cases, because right now these tests we emit have some complications with test oracles. And that's it. Thank you. I understand that this might be complicated work, so probably you might have some questions. I'm really glad to answer to them.
Sure, Alexei, thank you very much. Interesting presentation, interesting work. A few questions. First, did you compare yourself with existing symbolic execution solutions for JavaScript and TypeScript?
It's quite complicated. Yeah, it's quite complicated because usually they focus on a particular issue. For example, they want to find some injections in some SQL instructions, and they completely design their symbolic engine just for this task. Another issue was that mainly this engine has some limitations since its focus is ArkTS and ArkTS applications, and we had make some limitations due to these semantics. So we make some approximations for TypeScript, which is completely accurate for ArkTS because it's this construction is prohibited. So no, we don't have the exact numbers because as for me, it seems like a bit different tools.
Interesting. And your tool is already available for, let's say, JavaScript projects?
Yeah, you can use Arc Analyzer tool I mentioned. It's open source. You can use it to translate from JavaScript files into ArkER, and after this, you can use this tool.
Okay. And this translation, it works for any JavaScript programs?
I'm not sure about any JavaScript programs because how ArkTS works. You have two parts. You have parts written in ArkTS, and you might have parts written in JavaScript and TypeScript. And I'm not sure that it works on every JavaScript, but on JavaScript we tested, yes, it worked, but I'm not sure.
And also in your presentation, you said that your key novelty is in the introduction of this specific, like a fake type or the fake element, which you pass as an argument, which assembles together all the possible possibilities. Yeah, like all the options which may be present there. So I'm asking, is it something that no other symbolic execution engines have? Is it really on your new idea?
Yeah, seems impossible to find this where it was.
Next, further. It was slide like 15 or something. More. Next.
It's here.
Yeah, this one.
I think yes. It's quite complicated because in SMT you have several limitations. For example, you know that if an else expression, both its branches should have the same type, but you don't have in SMT the same type for number and reference, for example, or number and Boolean. And you need to understand how to implement all the operations with two main purposes. You don't want to have path explosion, and as I know, this exact issue all other tools have. So, for example, because of this, they have really low performance in many cases. Another approach is just to somehow over-approximate it. So to restrict some operations. For example, you know that Boolean and string can produce only string, and number and string can produce number as well. I think not only string, but you have some coercion rules, and they limit these coercion rules. We tried to get the whole picture and try to implement it if then else chains to avoid additional forks, so we can reduce path explosion.
So this indeed is innovative. Definitely.
As far as I know, yes. It's quite complicated because you cannot see too many symbolic engines for any languages and for JavaScript as well. And it's complicated to understand limitations of each approach. So as far I know, yes, it's a novelty.
Okay, then we wish you success in your future studies in the same
Thank you.
direction and hope to see you again at our conference.
Thank you.